So this is the second video in this series of 2 videos about intermodulation distortion. The first we talked about was amplitude distortion, or amplitude modulation, excuse me, and now this video is going to be about frequency modulation. So amplitude distortion, or amplitude modulation, was like a sine times a sine type of thing. But here we're going to have like a sine of a sine kind of thing. So the argument to our trig function is itself going to be something that is oscillating. So if you think about drawing your closed parenthesis right here, this is what we very often look at, just a cosine function with an argument, omega 1, and t is often a vector, but it's monotonically increasing. Whereas now we're passing in this argument that is itself a trig function. So at any given moment in time, at every sample, we're adding something to omega 1, and that thing we're adding to it is itself moving up and down. It's oscillating. So omega 1 is constantly changing. Omega 1 is constantly moving up and down as dictated by a2. So sine itself is bound between negative 1 and 1, multiplied by a2, so now it's bound by negative a2 to positive a2. So omega 1 might swing as high as omega 1 plus a2 and as low as omega 1 minus a2. So we can create really small shifts in frequency or really large shifts in frequency that's dictated by this scalar a2. And there's a Bessel function identity we can use here to expand this out. So it's, again, not necessarily very intuitive what frequency components are going to show up when we see this. We can really only say for sure what frequency components are going to show up when we see a kind of traditional trig function, you know, just a cosine of omega 1 times t or a sine of omega 1 times t. Adding this other trig function as the argument to cosine should leave you scratching your head, well, what components are actually going to show up in the frequency domain? And so this is a Bessel identity, and for anyone who doesn't know, this J naught is basically the Bessel function, and it's kind of written a little weirdly, I think, to me honestly. The subscript should basically just be another input argument to the Bessel function. So the Bessel function basically has 2 arguments, let's call them n and beta, and so the argument n is the subscript and the argument beta is a2. In every case, the second argument is just this scalar offset to the sine function. So rest assured that just, you know, j naught of a2 is a scalar, j1 of a2 is a scalar. These are all just scalar coefficients to trig functions. And yeah, just think of the subscripts as another input. So it's very easy to know j sub n of beta. It's very easy to know that the Bessel function itself is a Bessel function of the first kind is well defined. So we're going to expand this out again as we did in the last video. So this whole thing is just a scalar coefficient. J sub 1 of a2 times a1, that's all just a scalar coefficient, and it's being multiplied by this difference term and by this sum term, as are all these coefficients. So when we expand this, this is going to reveal a pattern that will become useful. We have this negative j sub 1 term, positive j sub 1 term, negative j sub 2 term, positive j sub 2 term, on and on. And what that's going to allow us to do is use this summation, which is very compact, to describe all these frequencies, and there should be an ellipses here, dot, dot, dot. This goes on forever. And this, you know, n equals negative infinity to infinity encapsulates that very nicely. So if you're shrewd, you might see that, well, hold on, this means we'll have a j sub negative 1 and a j sub negative 2 and a j sub negative 3 term, and we will, but rest assured that the j sub negative 1 term is just equal to negative 1 times j sub 1, and on and on. So that's how we get, from here, that's how we actually get these terms with these negative coefficients, the negative j sub 1 and the negative j sub 2 and the negative j sub 3, on and on. This is really useful, and what it also makes really obvious is that this thing here, this really compact thing, when we look at it as all of its individual frequency components, there are infinitely many frequency components. and that doesn't mean that all of them are in the audio band, or it doesn't mean that all of them have a non-trivial amplitude, but there are theoretically infinitely many frequency components, and we'll see how many of them matter. We can do from n equals -1 to 1 and n equals -2 to 2 to kind of step our way up, increasing in order to see how many of those frequency components really matter. So, and of course, I couldn't do this with all of its infinitely many frequency components, at least not this method. Again, this simple mathematics does theoretically include all these infinitely many components, but I'm going to do both methods and we'll show how they compare to one another. So this is the simpler method, just the cosine of omega 1 plus sine omega 2. And then this is the summation method, going from -n to n and using the Bessel function. And you can see actually here in octave, the Bessel function has two inputs, n and a2. So like I said, that subscript is more like an input than anything. So we'll start with just n equals 0, so this will just be a single term. So this is just for n equals, spoiler, -0 to 0 is just 0. And that's just going to give us a single frequency at f1, at 201 hertz. So you can see that's kind of the fundamental frequency of the more complex waveform. And of course, the more complex waveform has all these additional components, which we can see in the time domain. But when we just do this 0th order evaluation, we just get this one fundamental frequency. And so then we can step up. First order, we now added two more terms, the terms at -1 and 1. Add these two additional components here, and we can see now already all of a sudden in the time domain things look really closely matched, and that's because the components that I've accounted for are at most 30 dB down from the fundamental already. So these really are starting to not matter. These components are starting to not matter. You can see in the time domain things are already really close, but let's just step up two more times. You can see these additional pairs of components get taken care of as I step up to second order and then third order. And now, I mean, things are just really, really, really close to one another. And as I showed previously, I'll show the production of an undertone. So again, if we make these two frequencies closer together, then what we're going to have is this term that's at n equals -1, and we'll show the exact term. Here is the exact term. We have omega 1 minus omega 2. So again, almost the same as what we had in the previous example in the amplitude modulation video. The coefficient is a little different. The coefficient is what's dictated by the Bessel function, but the frequency is the same. It's 56 hertz. So this is another way that you can generate an undertone with intermodulation distortion, a different type of intermodulation distortion, but both amplitude modulation and frequency modulation can produce these undertones. So yeah, that's the end of this video. If you want a better understanding of the way that the original kind of cosine of omega plus sine of omega creates that infinite sum of Bessel functions, I'll put a link in the description. It's certainly not necessarily a very intuitive identity. I certainly couldn't prove it from scratch myself, but it's a well understood and documented phenomenon. And so I'll put a pretty good link in the description if you want to understand the maths behind that a little better.